Welcome to EDU World Space.
In a solar eclipse, the moon, earth, and sun are in a same line. So the moon is between the earth and the sun. So the force exerted by the sun on the moon is what we need first. So A, force equals G M over R squared. So in this case, we're going to have, obviously in all cases, G is 6.67 times 10 to the negative 11th power in SI base units. Capital M would be the mass of the sun. The mass of the sun is 1.99 times 10 to the 30th power in SI base units, which are kilograms. Mass of the moon. Let's see if I have this written down. I believe that I do not have this written down, so I'm going to Google it. Mass of the moon in kilograms is 7.35 times 10 to the 22nd power kilograms. And I'm going to write capital R is from Earth to Sun. 149.6 times 10 to the 9th power meters. And then I'm going to do lowercase r, which is from Earth to the moon. Radius from Earth to moon. In kilometers or in meters. I'm just Googling this. It says that it is 1,737 kilometers. But kilometers are times 10 to the third power. So I'm going to erase that. And I'm going to write times 10 to the third power meters. Now, I need to adjust my generic equation here. The denominator is going to be radius from sun to earth minus radius from moon to earth, which is probably negligible anyway, and then squared. GMM over R minus R squared. I'm going to put this in a calculator, and I'm just going to use all the numbers that I've written down for you. And so 6.67 times 10 to the negative 11th power times 1.99 times 10 to the 30th power times 7.35 times 10 to the 22nd power. All of that divided by the quantity 149.6 times 10 to the 9th power minus 1,737 times 10 to the third power squared. And this gives me two significant digits, 4.36 times 10 to the 20th power newtons. I'm just going to take away the radius little r and see if that really makes any difference. If you take little r away, oh, darn it. There we go. If you take little r away, it gives you 4.36 also. So, little r is really negligible. It is very, very small compared to big R. And that's interesting to note. B. Force on the Earth. So in part B, we're going to replace this M with the mass of the Earth. Mass of the Earth is 5.97 times 10 to the 24th kilograms. And since little r was negligible, it's really the same equation. So all I have to do is write F equals G M E, that's an E, over R squared. Put that into a calculator. 5.97 times 10 to the 24th power Oh, looks like I actually just solved C. I was getting ahead of myself, apparently. So this is actually C, the force of the sun on the Earth. And I did get an answer of 3.54 times 10 to the 22nd power newtons. So let's look at what B was. Apparently I skipped B. I read C instead. B is asking us about Earth on the moon. So Earth on the moon. So F equals G. This has to be mass Earth, mass moon over the radius Earth moon. That's little r squared. So mass Earth, this is mass of the moon, and little r. So I have to put those in. So let me go ahead and do that. Okay, I already have mass Earth in from the last problem, so now I need mass of the moon. 7.35 times 10 to the 22nd power. Over R. This time R is little r. 1737 times 10 to the third power squared. I put all of these in a calculator and I get 9.70 times 10 to the 24th power newtons. So the last part asks us why the sun doesn't pull the moon away from the Earth. Well, the force exerted by the sun on the moon is A. And we can see that that is to the 20th power. The force exerted by the Earth on the moon is B. That's to the 24th power. And so the force exerted by the Earth, this is in D, force exerted by the Earth is much greater than the force exerted by the sun on the moon.